Look at a massive steel bridge as a fully loaded freight train rolls across it. The metal appears entirely static, unyielding to the weight overhead. Thousands of tons of freight and gravity drive downward, relentlessly trying to push the structure into the river below. Despite these massive external forces, the steel doesn't simply fold or give way. The material survives by maintaining a state of static equilibrium, a condition where the bridge actively fights back against the train. This stillness is a functional stalemate. The structure remains standing because it generates internal forces that perfectly mirror the external weight. This cross-section reveals the first internal defender, shear force. As the external load pushes down on the beam, internal shear forces act parallel to the cross-section, pushing back vertically to prevent the structure from slicing apart. The heavy weight also forces the span downward, attempting to curve the metal. To resist bowing, the beam generates a second defender, the bending moment. This internal rotational force pushes back against the downward curve. We define a bending moment as a force multiplied by its distance from the pivot point, acting perpendicular to the cross-section of the element. This internal counterpunch is what keeps a beam rigid and functional under massive pressure. To see how this rotational punch works, we have to look straight down the barrel of the beam at the individual material fibers. Notice what happens to the top half of the beam as it bends downward. These fibers are forced together, creating internal compressive forces that crush inward. At the same time, the material fibers along the bottom are being pulled apart, creating internal tensile forces. The exact center line between this crushing and stretching is called the neutral axis. Because the fibers here experience zero change in length, this specific plane exists in a state of zero stress. This simultaneous push at the top and pull at the bottom creates a force couple. These two opposing actions link together around the neutral axis to form the total bending moment. This state, compression on top, tension on the bottom, is called sagging. It creates a positive bending moment, found at the center of a loaded span. Near a support column, these forces invert. The beam drapes over the pillar, stretching the top fibers and crushing the bottom. This is called hogging, and it creates a negative bending moment. Between the support and the center span sits the point of contraflexure. At this specific location, the beam transitions from hogging to sagging, and the internal bending moment is exactly zero. Every structural element contains this network of internal stress states, shifting and adapting to the loads above. Engineers design structures to withstand the most dangerous point on the span. This usually occurs at the center, where the shear force drops to zero and the bending moment reaches its maximum magnitude. If internal tensile stresses exceed the material's yield strength, the steel undergoes flexural yielding. It stretches permanently until fibers fracture and the beam fails. Engineers predict failures using a bending moment diagram, plotting internal moments along the structure. This aligns mathematical peaks with physical locations, showing where forces are intense. Designers optimize the structure, thickening material in high-stress zones and thinning it where the moment drops. This optimization allows engineers to manipulate geometry and trace the path of invisible forces, safely holding the line against gravity.